Hey y'all, so I just took a picture of this and I'm going to send it along with this video, but I'm going to go through it and show you guys how to do the assigning charges to a peptide thing for the quiz. So, okay, I'll go through what I wrote down and just kind of explain it thing by thing. So, actually, this will make more sense once we do the example, but a main point to understand for this quiz is that whenever you are protonating an amino acid, you're only protonating the R group. Right, so we know that the R group is the differentiable group that's different on each amino acid. You're not protonating like the carboxyl terminus or the amino terminus, you're doing the R group. So basically, if you're protonating an R group for every single amino acid except for the amines, when you protonate it, it's going to become neutral. So if you think about like this one, so it has a negative carboxyl group. If you add an H, it's going to become neutral. The only ones that become positive are the amines. And so if you look at this one, if you add an H to this N, which is happy there with 5 electrons, then it's going to lose an electron because it gained a proton, and it's going to become positive. So, and I mean, you don't really need to know the specific reason it does that, but just know like amines are going to be the ones that become positively charged, and that'll make more sense in a second. Okay, so this is the rules for calculating the charge of a peptide. So I'm going to go through the example that was on the PowerPoint. It's on slide 11, I think. Okay, so the first thing that you do is you figure out which amino acids have R groups that can be charged. So what does that mean? It means that you can add or remove a proton from the R group. So if we look at this example, for example, alanine, you wouldn't be able to take a H off of a CH3, right, a methyl group, because it's happy. A C isn't a electronegative atom, right? It's pretty neutral, it's organic. So it's going to share its electrons pretty evenly. In other words, it's not going to hoard them like an oxygen over here where all the electrons are going over towards the oxygen, so you could just pull the proton off. So that's why you never see like, you know, like CH2 minus or whatever. You never see that because C isn't an electronegative atom. So anytime you see just a nonpolar like organic, you know, carbon group like alanine or glycine just has an H, it can't be charged because you can't move around the proton. Over here, on the other hand, you can take the H off the O, which hopefully, like, you know, we know from like organic chemistry, but you could do that for oxygen or nitrogen or sulfur because those are all electronegative and they're going to be pulling those electrons, so you can take the proton off. Okay, so once you go through and you figure out which ones are charged, then you assume that the left end is the amino terminus and the right is the carboxyl terminus. So, like for example, we'll go through this in a second, but on my far left, I'm going to know that this alanine, even though it is not able to be charged because of the methyl group right there, we're going to know that the alanine has a +1 charge because it's on the very end. And not in the R group, but over here on the amino group, it's going to have a plus charge just because of the way that amino acids are structured. So over here, this alanine is going to have a plus charge, and over here, this carboxyl terminus, this alanine is going to have a negative charge. Because again, like, you know, this carboxyl group, the O doesn't have a proton over on the end. Okay, so once you do those two things, then it's pretty easy. I just set up this little table, which I would recommend doing, but like, I guess you can do it in your head too if you want. But so basically, first step, so we find which amino acids have the R group that can be charged. Okay, so alanine we know under certain circumstances can't be charged, but again, it's amino acid, or it's the amino terminal, so we're gonna know that anything on the far left end has a +1 charge. Glycine, if we remember, it's just got an H as its R group, so obviously like you can't take that one H off, so we're gonna leave that alone. And I'm just circling all the ones that can be charged. Aspartic acid, and I'll show you this, I have them on flashcards. This is the structure of aspartic acid. So we know that that can be charged, right, because you can add or take away, or you can add a proton onto this oxygen, because oxygen is electronegative. So we're going to circle that because we know we're going to deal with that. We go on to cysteine. Here's a picture of cysteine. We know that you can move the hydrogen away from the S because, again, S is electronegative. So the three elements that you have to remember, and it's the only 3 that are in amino acids, are oxygen, nitrogen, and sulfur. So if you see those in an R group, those are going to be charged, or like have the ability of being charged. If you see just a carbon or anything like just organic, it can't be. So cysteine can be charged, so we circle that. And over here is another cysteine, we circle that, same thing. Let's see, glutamic acid. This is the structure. Okay, so oxygen can be charged. And then again, leucine and valine. If you guys just need like a update. This is leucine, so it's all organic, all C's, can't be charged, can't take an H off of a C. And then valine is the same way. So we're going to leave those two alone. Alanine we've already went through, can't be charged, but this alanine on the end, we're like, okay, it's on the end, on the right terminus, so we know that's the carboxyl terminus. So that's going to have the negative charge. Okay, so now we know which ones we're dealing with, so we just go through, and on this little chart thing that I made, you're just going to fill in the gaps. So the ones on the end, you can leave those alone unless like it was a cysteine on the end or something, like something that had a capability by itself to be charged. But if it's just charged because it's on a terminus, you don't have to worry about any of that. You just put the charge that we know is going to be there because it's on the terminus. Okay, so aspartic acid, the pKa, he's going to give you the pKa value. So like over here, aspartic acid is 3.9. So we just write that in our chart. And then this is where the rules on the top become relevant. So if our pH is greater than our pK, then it's not protonated. Okay, it's just left alone like we know how it is. If the pH is less than the pKa, then it is protonated. So over here, oh, and I forgot to mention that for each example, like he'll give you a chain of amino acids, and then he'll give you a certain pH. So if it's at pH of 7, then that's the pH that we're going to compare our pKa to. So right here, pH of 7 is greater than 3.9. So if our pH is greater than our pKa, then it's not protonated. Okay, so we put a no in that protonated box. And if we look at the, where did it go? If we look at the structure of aspartic acid, if it's not protonated, then it's going to have a -1 charge, right? We can ignore unless they're on the terminus, these two are going to cancel each other out, so it's neutral. So that's why you call it a charged amino acid, because really the R group is the only thing that's making the amino acid overall charged. So it's not protonated, so that there's not going to be an H connected to that O, so it's going to have a -1 charge, and that's why we put -1 right here. Okay, cysteine going on. We look at our little thing. Cysteine up here has a 8.3 pKa, so we put that in our little thing. Okay, so is our pH of 7 that he gave us, is that greater than our pKa of 8.3 or less? It's less. 7 is less than 8.3, so it's going to be protonated. So if you look at the structure of cysteine, then it's going to be protonated. Okay, so this used to confuse me. It doesn't mean, like, protonated doesn't mean that you take the structure that you memorize, like we all had to memorize these back in cell or whatever, and you add another proton onto it. So it's not going to be SH2. Protonated just means that if there's a spot for there to put a proton on, like, let's see, back on aspartic acid, there's a spot to put a proton on, then there's going to be a proton, okay? Or deprotonated means you take it off. But if we're looking at cysteine and we did our little rule and we're like, oh, okay, it's protonated, then we look at it and we're like, okay, so this is going to be the structure because it's already protonated. Don't try to add another H somehow. It's either protonated or it's got a minus sign, it's unprotonated. So we put a yes, and then we know just by looking at that there's no charge to it, so our charge is going to be neutral. Leucine and valine we skipped, and then and then glutamic acid. We go to our chart, it's 4.3, whatever that is, yeah, 4.3. So we put that in our chart. Is 4.3 greater than or less than the pH? It's less than, because our pH of 7 is greater than 4.3, so it's not protonated. So if you go and you look at your glutamic acid, amino acid, it's not protonated. There's not going to be an H in that little spot right there, so it's going to have a -1 charge. Okay, so we put the -1 here. Cysteine we already did, it's the same thing, so we just copy our information over here. And then alanine, again, don't do anything with it except for know that it's a -1 charge because it's on the far right, so it's a carboxyl. It's on the carboxyl terminus. And then the last step is that you just add them together. So we take +1, -1 is 0, +0 is 0, -1 is -1, minus another 1 is -2. Okay, and so that would be the charge of the overall peptide. Okay, let me know if you guys have any questions.